You are moving right now, not in the way it feels, in the way physics means it. The ground beneath this building is sweeping eastward through space. Depending on where you are on Earth, your latitude, you are traveling somewhere between 0 and 1,670 kilometers per hour, just from the planet rotating. That's faster than a commercial aircraft, faster than the speed of sound. You feel none of it, not one vibration. Here's what's stranger. That's just the rotation. The Earth is also orbiting the Sun at 30 kilometers per second. That's 107,000 kilometers an hour. And the Sun itself is moving through the local stellar neighborhood at 20 kilometers per second. And the entire solar system is orbiting the center of the Milky Way at 220 kilometers per second. And the Milky Way is falling toward a gravitational attractor 250 million light-years away at 600 kilometers per second. Add it all up, measure it against the oldest light in the universe, and the number you get is about 370 kilometers per second. That's us, right now, moving through the background radiation of the cosmos at 370 kilometers per second. And the only thing you can feel is your heartbeat. Before we had telescopes, we had a sky that moved. Every culture on Earth noticed it, and most of them got the reason exactly backwards. They thought the stars were spinning around a stationary Earth. They were wrong about the cause, but they were right about something important. Everything is spinning. They just didn't know how deep that goes. Here's where it actually starts. Not with planets, not with solar systems, but with a cloud. A molecular cloud. Hydrogen gas and dust spread across light years of space. Cold, dark, almost nothing, and rotating so slowly that if you were inside it, you would have absolutely no sense of turning at all. The rotation period of these clouds can be hundreds of millions of years, but the rotation is there. And what happens when gravity gets involved with a slowly rotating cloud is one of the most consequential physics facts in the universe. When the cloud starts to collapse, when an overdense region gets a little heavier than its surroundings and gravity starts pulling everything inward, the rotation doesn't go away. Can't. There's a rule that forbids it. Angular momentum. Angular momentum is the product of how much mass is spinning, how fast, and how far that mass sits from the center. And the universe has a strict policy. The total stays constant. You cannot create it. You cannot destroy it. You can only move it around. So when the cloud collapses, when that radius, that distance from the center, drops by a factor of trillions, the velocity has no choice. It has to skyrocket. This is why you've seen the shape before. Not a sphere, a disk, flat, thin, spinning. Gravity pulls inward equally from all directions, but the rotation pushes back, specifically outward from the plane of spin. Inward along the axis, gravity wins. Outward along the equator, rotation resists. The cloud pancakes, thins, spreads. And at the center, where density peaks and pressure is greatest, a star ignites. Around it, the leftovers, rings of gas and rock, still spinning, still carrying the angular momentum of the original cloud. Over millions of years, those rings clump together. Gravity plus patience equals planets. Each one orbiting the star in the same direction the original cloud was rotating. Each one spinning on its own axis for the same reason. Because there was never any force to stop them. This is the solar system you live in. Every planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, orbiting the same direction. Counterclockwise, viewed from above the sun's north pole. Not by accident, by inheritance. The molecular cloud that collapsed to make all of this was rotating counterclockwise. It passed that preference down to everything. The disk is the spin made visible. But two things didn't get the memo, and they're worth paying attention to. Venus rotates backward. Not in its orbit. Venus politely orbits the sun counterclockwise like everyone else. But its spin, its rotation on its own axis goes the other way. Slowly. One Venusian day lasts 243 Earth days. Longer than a Venusian year. And it runs in the wrong direction. On Venus, the sun rises in the west. Uranus is tilted 98 degrees. It doesn't spin upright. It rolls around the sun on its side, its poles pointing toward and away from the sun over the course of its orbit. The best explanation for both impacts. Something large, possibly Earth mass in Uranus's case, hit these planets at the right angle at the right moment in the early chaos of solar system formation and scrambled their rotation. Here's what's important about that. It's not a violation of the physics. The total angular momentum of the solar system still balances. Something else is spinning a little differently because of those impacts. The books are always balanced. Always. You've seen this before. A figure skater on ice, arms extended wide, spinning slowly. The arms come in and she speeds up. No new force arrived. The ice is the same ice. She just got smaller, and getting smaller made her faster. This is angular momentum conservation working at human scale, in human time, where you can watch it happen in real time. It's the reason physicists keep coming back to this example. Not because it's elegant, but because it works. Here's what it actually means. The speed was already there, latent, stored in the relationship between her mass and how far it sat from the axis she was spinning around. When she pulled her arms in, she didn't generate speed. She revealed it. Angular momentum doesn't dissipate like heat does. It doesn't radiate away. You can move it, redistribute it, but you cannot make less of it. The universe has kept the same total angular momentum since whatever initial conditions produced it. Now take that skater and scale it up. A molecular cloud hundreds of light years across, rotating once every few 100 million years. You'd have no sensation of rotation inside it. Nothing inside it would notice. But gravity finds an overdense region. The collapse begins. The cloud gets smaller. The rotation speeds up. You're compressing something by a factor of trillions. The angular momentum doesn't go anywhere. The rotation doesn't just increase, it dominates. It starts shaping everything. That disk, the reason solar systems are flat, is what happens when spin meets gravity at that scale. The shape isn't incidental. It's a physical record of which direction things were rotating when they collapsed. This is why Saturn's rings are flat, why galaxies are flat. The shape is the same at every scale because the physics is the same at every scale. But here's where the ice skater analogy runs out of room. When a star 8 to 20 times the mass of our sun exhausts its fuel, something happens that takes about 1 second and is, by any reasonable measure, the most extreme event that regularly occurs in the universe. For millions of years, that star has been held up by nuclear fusion, the ongoing conversion of lighter elements into heavier ones, releasing energy, pushing back against the inward crush of hundreds of millions of kilometers of stellar mass sitting on top. That balance is the star. The fusion moves outward through the periodic table. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, each stage shorter than the last, requiring more pressure, producing less energy per reaction. Silicon burning lasts about 1 day, after millions of years of hydrogen. After progressively shorter, hotter, more desperate burning stages, the final stage of nuclear burning in a massive star's core lasts approximately 1 day, and it produces iron. Iron is where the negotiation ends. Fusing iron doesn't release energy, consumes it. Iron sits at the bottom of what physicists call the nuclear binding energy curve. It is, in a very precise thermodynamic sense, the most stable nucleus. You cannot extract energy from it by fusing it into something heavier. You cannot extract energy from it by splitting it into something lighter. It just sits there, accumulating in the core, producing no outward pressure. The core, roughly the mass of our sun, compressed into a sphere about the size of Earth, crosses a threshold called the Chandrasekhar limit. About 1.4 solar masses. The quantum mechanical stubbornness that was holding it up fails. What happens next takes less than a second. The outer edge of the iron core is falling inward at 70,000 kilometers per second, a quarter of the speed of light. Within the first fraction of that second, the entire core, the size of Earth moments ago, collapses to something approximately 20 kilometers across. 20 kilometers. You could drive across it in about 12 minutes. A teaspoon of this material weighs roughly 1 billion tons. This is a neutron star. And now the ice skater at maximum. The progenitor star was rotating slowly, maybe like our sun, once every few weeks. When the core collapsed from Earth's size to 20 kilometers across, that angular momentum had to go somewhere. It went into the rotation. A neutron star can spin hundreds of times per second. Not per minute, per second. The fastest known, called millisecond pulsars, rotate over 700 times per second. The surface of such an object is moving at a significant fraction of the speed of light. The same mechanism as the ice skater. The same physics. But so many orders of magnitude beyond that analogy that the analogy starts to feel almost embarrassing. The skater brings her arms in by maybe 2 meters. The stellar core brings everything in by a factor of tens of thousands. And the angular momentum doesn't change. The rotation speed has no choice but to become that. These objects emit beams of electromagnetic radiation from their magnetic poles, which are often not aligned with the rotation axis. As the neutron star spins, those beams sweep through space like a lighthouse. If Earth is in the path, we detect a pulse. Once per rotation, hundreds of times per second in some cases. The timing of these pulses is extraordinary. Millisecond pulsars are among the most stable clocks in the known universe. More stable, in some cases, than atomic clocks on Earth. We use pulsars to detect gravitational waves. A dead star spinning in the dark, keeping better time than anything humans have ever built. That's what angular momentum preservation looks like at its most extreme. The moon is leaving. Not quickly. About 3.8 centimeters per year, roughly the same rate your fingernails grow. But it's leaving. And it's been leaving since it formed, about 4.5 billion years ago. The mechanism is called tidal friction, and it is, without any exaggeration, one of the most consequential ongoing physical processes affecting life on Earth. Gravity doesn't pull uniformly on an extended object. The side of Earth facing the moon is pulled slightly harder than the center of Earth, which is pulled slightly harder than the far side. That difference, that gradient across Earth's diameter, is the tidal force. It physically stretches the Earth into a very slightly elongated shape. A bulge pointing toward the moon, and a corresponding bulge on the opposite side. The oceans show this obviously. The solid ground shows it too. The bedrock under your feet flexes about 30 centimeters twice a day as the moon passes overhead. Here's the part that transfers angular momentum. Earth rotates faster than the moon orbits. One full rotation of Earth, 24 hours. One full orbit of the moon, about 27 days. So Earth is constantly spinning the tidal bulge forward, pulling it slightly ahead of the Earth-Moon line. That offset bulge exerts a gravitational pull on the moon. A persistent pull, ever so slightly in the direction of the moon's orbital motion, that nudges the moon into a slightly higher, slightly larger orbit. The moon gets farther away. Meanwhile, the moon's gravity pulling back on that offset bulge slows Earth's rotation. Torque. Angular momentum being drained from Earth's spin and deposited into lunar orbital energy. The total stays constant. It always stays constant. The numbers on this are real and specific. 400 million years ago, in the Devonian period, when the first vertebrates were crawling onto land, a day on Earth was about 21 to 22 hours long. Earth was spinning faster. That gave the Devonian year approximately 400 days. We know this from fossil coral. Coral records daily growth rings and annual patterns in those rings. Count the daily rings within one annual cycle, and you get the number of days in a Devonian year. You can hold a piece of ancient coral and read the length of a day from 400 million years ago inside it. Go further back, about 1 billion years after Earth's formation, and the moon may have been a third of its current distance. A day might have been 6 hours, maybe less. The moon would have been visibly, unsettlingly larger in the sky, and the tides would have been enormous. Not ankle-deep at the shore enormous. Reshaped coastlines enormous. Some researchers think the rhythmic wetting and drying of early tidal pools, cycling organic molecules through concentration and dilution and back again, may have had something to do with how life started. That's speculative, worth saying plainly, but the mechanism is physically real. And the moon itself is the endpoint of this process applied to a smaller body. The same tidal friction that's slowing Earth's rotation already ran to completion on the moon billions of years ago. Earth raised tidal bulges in the moon. The same angular momentum transfer happened. The moon's rotation slowed until it matched its orbital period exactly. One face toward Earth. Always. The far side perpetually turned away. If the Earth-Moon system had enough time, longer than the Sun has left to burn, they would reach mutual tidal lock. The same face of Earth always pointing at the Moon. The same face of the Moon always pointing at Earth. Two bodies staring at each other across a fixed distance, rotating together as one system. The angular momentum fully redistributed. The trade complete. It won't happen. The Sun will become a red giant before the lock completes. But it has happened elsewhere in the solar system. Pluto and Charon are mutually tidally locked. Charon is so massive relative to Pluto that they're more accurately described as a binary system. Two bodies orbiting a common center of mass that sits outside Pluto's surface. They face each other permanently. If you stood on the hemisphere of Pluto facing Charon, Charon would sit fixed in the sky, never rising, never setting, just there, going through phases as the Sun moved. Walk to the other hemisphere and Charon would never appear. You'd live your whole life on that side without ever seeing the largest thing in Pluto's sky. The angular momentum transfer ran to completion. The negotiation is finished. Tidal forces don't only slow things. At close enough range, they tear. When an object drifts inside what's called the Roche limit, the tidal force across it exceeds its own internal gravity. The differential pull becomes greater than the tensile strength of the object. The near side experiences meaningfully stronger gravity than the far side. The object stops being one thing and becomes many smaller things. Saturn's rings are, in one sense, a tidal friction casualty, something that got too close. The differential pull exceeded what held it together, and the object spread into the ring structure you can see from Earth with a decent telescope. A spectacular outcome of the same physics that moves the Moon one fingernail's width per year. The most recognizable shape in astronomy. You've seen it on posters, in textbooks, in the background of every science documentary. It has become almost decorative, a visual shorthand for cosmos, which is a shame, because the actual story of why galaxies are spiral-shaped is genuinely strange, and the familiarity of the image makes it easy to assume the explanation is equally familiar. It isn't. The arms are not what they look like. For a long time, astronomers assumed the spiral arms were rigid structures, fixed groupings of stars rotating together, like spokes on a wheel. That can't be right. The center of a galaxy rotates faster than the outer regions. If the arms were material structures, the inner parts would race ahead of the outer parts, winding the arms tighter and tighter with every rotation. In a few 100 million years, the arms would be wound into an indistinguishable blur. Galaxies are billions of years old. Their arms are not wound up. The resolution worked out by C.C. Lin and Frank Hsu in the 1960s. The spiral arms are not material structures at all. They're density waves, patterns of compression that move through the disk independently of the stars themselves. Think of a long exposure photograph of a highway at night. The streaks of headlights and taillights in that image aren't cars. The cars have moved, are elsewhere by the time the shutter closes. The streaks are a record of a pattern, a density in the road. Spiral arms are like that. Stars and gas enter the arm, get slowed by the slightly higher gravitational density there, pile up briefly. In that piling up, the gas compresses, triggers star formation, produces the brilliant young blue stars that make the arms luminous. Then the stars drift through and out the other side, carrying on in their individual orbits. The arm isn't those stars. The arm is the compression region, a standing wave in the rotating disk. Now here's where the rotation reveals something unexpected. When astronomers in the mid-20th century began measuring how fast different parts of spiral galaxies rotate, plotting orbital velocity against distance from the center, they expected the same pattern as the solar system. Closer to center, faster. Further out, slower. Mercury moves faster than Earth, Earth faster than Mars. Simple Newtonian gravity from a central mass concentration. The measurements showed something completely different. The rotation curves of spiral galaxies are flat, not declining. Stars at the outer edges orbit at roughly the same speed as stars much closer to the center. In some galaxies, the curve rises slightly before flattening. In almost none does it fall the way it should, given the visible mass. The outer stars of a typical spiral galaxy are moving 2 to 3 times faster than the visible mass of that galaxy can gravitationally support. Something is providing extra gravity. Something we can't see. Dark matter. Not a particularly informative name, it means, essentially, matter that doesn't interact with light. Matter invisible to every wavelength of electromagnetic radiation we can detect. We can't see it. We can't emit or absorb it. We infer its existence entirely from its gravitational effects. Current best estimate: dark matter makes up about 27% of the total energy content of the universe. Ordinary matter, everything you can see, every star and planet and gas cloud ever observed, makes up about 5%. The spiral galaxies we photograph so extensively are embedded in halos of dark matter that extend well beyond the visible disk, providing the gravitational scaffolding that keeps the outer stars moving at the speeds they move at. The arms, the thing that gives spiral galaxies their name, exist in a disk of ordinary matter that is a minority component of its own galaxy. The photograph shows you the arms. The arms are real, but they're also, in some sense, the least of what's there. In 2011, a study of around 15,000 spiral galaxies found a slight excess, about 7%, of galaxies spinning one direction over the other. Left-handed spirals slightly outnumbering right-handed ones. In 2020, a study of 200,000 galaxies found not just a rotational bias, but a multipole structure to it. A pattern that seemed to get stronger at larger distances, deeper into the past. The bias in that dataset was around 10%. 10% more galaxies spinning one way than the other. That number sits in an uncomfortable place. Too large to dismiss easily. Too small and too dependent on methodology to call definitive. If it's real, if galaxies across the observable universe do have a statistical preference for one spin direction, it would mean the early universe had a net angular momentum. That whatever conditions produced the Big Bang produced them with a spin already built in. That the universe was born rotating, or close enough to rotating that structure formation inherited a direction from it. The standard cosmological model predicts no preferred direction. A 10% rotational bias in galaxy spin would be a violation of isotropy, and not a small one. There are other anomalies pointing the same direction. The cosmic microwave background, the oldest light in the universe, mapped in extraordinary detail, has a cold spot in one hemisphere that standard cosmology doesn't fully explain. A slight asymmetry in temperature fluctuations between hemispheres. Several large-scale features that seem to align with each other in ways that shouldn't happen if the universe is truly uniform in every direction. Cosmologists have called this alignment, with the specific dry humor that comes from working on unsolved problems, the axis of evil. These anomalies might be statistical flukes. They might be contamination from our own galaxy, or they might be something real. We don't yet have the data to know. The spin doesn't stop at galaxies. Hold your left hand up, palm facing you. Now imagine the mirror image, not your right hand, the actual mirror image of the left. They look similar, but if you tried to stack them perfectly, palm to palm, finger to finger, they wouldn't match. They're the same shape in opposite orientations. Related by reflection, but not by rotation. This is chirality, the property of a thing that cannot be superimposed on its mirror image. Your hands are chiral. As it turns out, so is almost everything in your body. Amino acids, the molecular building blocks of every protein, the machinery of virtually everything biology does, exist in two mirror image forms. Left-handed and right-handed. In a chemistry laboratory, synthesize an amino acid from scratch with no biological input, and you get a 50-50 mixture. Equal amounts of both forms. The physics doesn't prefer one over the other. Life on Earth uses almost exclusively left-handed amino acids. Not mostly, almost exclusively. Every protein in your body, every enzyme, every structural molecule built from amino acids, assembled from left-handed forms. And it goes the other way for sugars. The deoxyribose in DNA, the sugar forming the backbone of the genetic molecule, is the right-handed form. The left-handed version functions fine in laboratory settings and is essentially absent from biology. Life went left for amino acids, right for sugars, and has maintained both choices across every living thing ever examined. Every bacterium, every plant, every animal. For billion years of biology across every branch of the tree of life, consistent handedness. The question underneath the name for this homochirality is why. 3 competing explanations. First, a coin flip. The first self-replicating chemistry happened to use left-handed amino acids by chance, and once it started replicating, it locked in. Right-handed life might have been equally viable. It just didn't win. Second, the weak nuclear force. One of the 4 fundamental forces of nature, it does not respect mirror symmetry. This was established experimentally in 1956. Electrons emitted by decaying cobalt-60 prefer one direction relative to their spin axis. Flip the experiment in a mirror and the physics is different. Left-handed and right-handed particles interact differently with the weak force. This creates an infinitesimally tiny energy difference between mirror image molecules, too small to measure in most contexts, but not zero. Whether it's large enough to have driven biological chirality over realistic timescales and environments is genuinely debated. Third, and this is where it gets strange, circularly polarized light from rotating neutron stars. Neutron stars emit radiation with a rotational component. Circularly polarized ultraviolet light can selectively destroy one mirror image form of an amino acid over the other. In laboratory settings, this has been demonstrated. If the interstellar medium from which our solar system formed was irradiated by neutron star emissions with a preferred circular polarization, if amino acid precursor molecules developed a slight chiral excess as a result, then the handedness of your proteins might trace back to the spin of a dead star. Meteorite analyses have found small left-handed excesses in certain amino acids, a few percent, up to 20% in some samples, consistent with presolar irradiation. The excess is in the rock. Where it came from is still being worked out. The origin is gone. We have the outcome, we have the physics, and we don't yet have the bridge between them. Nothing stops. That's the whole of it, really. Everything else in this film is just that sentence looked at from different angles, at different scales, in different light. The molecular cloud collapsed into a disk. The disk made a star and planets. A planet got the right chemistry. The chemistry was handed, left for proteins, right for DNA, possibly because of a dying star's spin, possibly because of a coin flip 4 billion years ago, possibly because of a fundamental asymmetry in the laws of nature themselves. That chemistry eventually produced things complex enough to notice they were spinning. And the moon is still leaving. 3.8 centimeters this year. 3.8 centimeters next year. The Earth's day is 1.4 milliseconds longer per century than it was. You won't detect this in your lifetime, but fossil coral records it one ring at a time. The angular momentum is moving from Earth's spin into lunar orbital energy, as it has every day since the moon formed, as it will every day for billions of years after every living thing currently on Earth is long gone. And in the very long future, time scales that require numbers where the exponents are large, the last objects in the universe will be black holes. They will be spinning, slowly losing their rotation to Hawking radiation over something like 10 to the power of 100 years. After that, nothing rotates, not because angular momentum was destroyed, because there is nothing left to carry it. But nothing is lost before then. Every rotation, every orbit, every spin, the Earth going around, the moon drifting, the spiral arms propagating, the pulsars keeping perfect time in the dark, all of it is the same angular momentum, the same total being passed around, redistributed, expressed in different forms, not diminished. The solar nebula's angular momentum is in the rotation of the Earth beneath you. The rotation of the Earth is in the drift of the moon above you. The drift of the moon is in the lengthening of the day, which is in the fossil coral record, which is in the rock beneath the soil, beneath the building, beneath the room you're in. And the handedness of the amino acids that make your proteins is in every motion your body makes, including the one going on in your chest right now. The one you can feel if you're quiet enough. The spin was there before anything had a name for it. Before the sun, before the planets, before the disk that made them. Some asymmetry in a gas cloud. Some slight net rotation, too small to notice. Waiting for gravity to find it and make it loud. And gravity did.